Alright guys, welcome to the next video and the final video of week 2 into molecular forces. This video is going to be quite long, but it's going to cover some of the main concepts in a little bit more detail. You are going to need to read the information here first as I'm going through it, and maybe even after the video, but you are going to have to review it and recap it because I just want to try and get this concept across to you because it's a little bit weird. So with intermolecular forces, there are 3 different types that you need to know. So I'm just going to abbreviate this to IMFs. And there are 3 that I'm just going to talk about in this video, and I'll explain in more detail, so don't worry. So you've got temporary dipole-induced dipole forces. We have permanent dipole-dipoles, and then we have H bonding. Many of you may have heard of some of these before, or maybe all of them, but they go in rank order. So temporary dipole-induced dipole forces are the weakest, and H bond are the strongest. The reason why I'm putting this here at the start of the video is many of you are going to come back to this video probably during revision, and this is the main key point that we need to take away. All molecules, or covalent molecules, have temporary dipole-induced dipole forces, as everything in the universe. Permanent dipole-dipoles only exist with things that are polar, and H bond is a very specific category of polar molecules that only works with HN, HF, and HO. But they are also permanent dipoles. They're just stronger versions, and we call those H-bonding. Right, let's go through some of the differences between intermolecular forces and bonds. This is one of the biggest misconceptions that I get from a lot of students almost every year, so I want to kind of break this down a little bit more. Let's take hydrogen. A molecule of hydrogen is H2, it's diatomic, and it's 2 non-metals, so therefore it's covalent. Shared pair of electrons attracted to opposite nuclei. So what we have here is a covalent bond. This keeps that molecule together. This is not an intermolecular force. This is an intramolecular bond. Intra means within, inter means outer, or outer side. Now, when I'm talking about intermolecular forces, I'm talking about the force it experiences next to another H2 molecule. So another one next to it. When these two come close to each other, how do they interact? They're surrounded by electrons. So we have a field of electrons orbiting them. So like this. And another field of orbitals like this with electrons in. Now, just as you guys can imagine, if I put 2 areas of electrons next to each other, what are they going to do? They're going to repel. Now, there is a little bit more to it than that. This repulsion is also combined with the fact that these electrons and orbitals slightly shift and move. So because they're not permanent and they can slightly shift and move, as you can imagine, when this gets closer, what's going to happen, let's try and do it this way to make it easier. As they get closer, what's going to happen is the electrons are going to repel ever so slightly like this. So they're going to shift kind of slightly away. And what we've done now is the molecule is no longer even. We have a side that is now slightly more negative. So we're going to call this delta negative, which means the other side must be delta positive. Now, because that's been induced by something else, it's only temporary because these electrons can shift. This is why we call this a temporary dipole-induced dipole force, because it's now been induced by something else. Now, because this is delta positive and the other one's delta negative, as you imagine, this one also can shift around. So I'm going to shift this one ever so slightly in this direction, maybe exaggerate it to prove a point. And now what you'll see is that this side is also delta negative, and this side is slightly delta positive. And now what we've got is a delta positive and a delta negative, which means, as you guessed, these two are going to very slightly attract each other. And that is the intermolecular force. So that slight attraction, it is the tiniest as you imagine. It is the slightest attraction, and that is what's going to keep those hydrogen molecules together. As you imagine, it's really, really weak. So any amount of temperature, which is the energy we put in, will break that force, and that's why hydrogen exists as a gas at room temperature, because even 25 degrees, the room that we're sat in, is far too much energy for hydrogen to become a liquid or even a solid. So that's what we're looking at with intermolecular forces. What you need to know is that all simple covalent molecules have this, and I imagine it a bit like a piece of Velcro around a molecule, and it gives a molecule a type of like stickiness, which is really, really low energy to overcome. They're small, but larger the molecules, so if it was a much bigger version, this doesn't exist, but let's pretend it was maybe like a carbon or something. Carbon is a much bigger atom, which means it's going to have more electrons, which means it's going to have stronger temporary dipole-induced dipole forces. The bigger it is, the more they have. The smaller it is, the less they have. And that's as simple as that. So, and you can see here, that's kind of how I've kind of slightly animated it as well. Now, I'm going to talk to you guys about permanent dipoles. So this is kind of recapping the polarity we talked about. And I'll tell you straight away, the only molecule that you definitely need to know is HCl. Hydrochloric acid has permanent dipole-dipole forces. It also has temporary dipole-induced dipole forces, but primarily permanent dipole-dipole forces. Let me explain. So when we look at HCl, if I go to the periodic table, you can see over here that typically where hydrogen is either here in the middle or there to the left. There is a large difference in electronegativity because they're far apart on the periodic table, which means they are polar molecules. So H and Cl are polar, they're far apart, so therefore it is a polar molecule, which means it can experience permanent dipole-dipole forces. Some of you might be thinking, yeah, but why? So let me have a look at those electrons whizzing around again. So we got this right here. Now I'm going to take a snapshot in time where the electrons are equally orbiting around this whole molecule. This doesn't exist, it's not true. But when I play this, what happens is chlorine is more electronegative, so it has a greater tendency to attract the electrons. So they are going to shift ever so slightly in favor to chlorine. Now chlorine's not changing its position on the periodic table. Look where it is. It's not moving. So the dipole isn't going to move. It's going to stay exactly where it is. And we're just going to call that permanent. It's a permanent dipole. The dipole is because we've got delta positive on hydrogen, which is basically always the case. And then we've got delta negative on chlorine, which is also basically always the case. So if you have chlorine in a molecule, it's typically going to be delta negative. If you have hydrogen in there, it's probably going to be delta positive. And that's permanent, which means when I have another molecule that comes in, another HCl molecule that comes in, bounces around, oh my God, it's going to be attracted to it. And maybe I should move the intermolecular force over here, and there we go. Now, because it's permanent, the electrons aren't really shifting away from each other like before, where they're going to shift away and break the bonds, so it's going to be quite hard to keep them together. In this one, it's permanent. So that positive and negative shift is always going to be there, which means they're always going to be slightly magnetized, I suppose. There's electrostatic attraction between them, and that's going to be quite hard. That's going to be more difficult to overcome. So you're going to have to require more energy to break that bond. Not a lot, but more. And if you think about HCl, hydrochloric acid, at room temperature, it's a liquid. You can see this in a beaker. It's a covalent molecule, but because it's got these strong permanent dipoles, it actually exists as a liquid at room temperature, even though it's a covalent molecule, which typically is a gas. But HCl will be a liquid because it's much harder to break those bonds, which means it's more fixed and therefore able to stay as liquid. Now this brings us on to some of the definitions. Again, you need to read these because I'm just trying to explain the concept to you, but they only exist in molecules that have electronegativities within the polar bond. So this red line is our covalent bond. We're not trying to break that. We're trying to break the intermolecular force, the thing in between them, to increase its boiling point, or to change its boiling, to reach its boiling point, sorry. So if I want to make it from a liquid to a gas, I need to break this bond, not this bond. And that's the difference. Lastly, we move on to hydrogen bonding. This is the same as permanent dipole-dipole. It only happens with polar molecules, but this only happens if a molecule has HN, HO, HF. And I just remember it as H bonding as HNOF. And that's typically how I remember it. So, for example, ammonia has got an NH bond, an NH bond, an NH bond. Water has an OH and an OH. So, because it's got these polar bonds, so an NH bond is polar, N is over here, H is over here, or sometimes over here. Large difference in electronegativity, therefore polar. It is also HN, therefore H bonding. It is also a simple covalent molecule, therefore temporary dipole-induced dipole force. It has all of them. If it's got H bonding, it's got every single one. Dead easy rule to remember, easy for you to take away. Now, water has some really special properties, which I'm going to cover in a minute, but before we do, I just want to summarize some of the common examples you will see with H bonding. Water, super favorite by everyone. Ammonia, really common. Alcohol is a really interesting one. And then you've got hydrogen fluoride. So the reason why alcohol is an interesting one is you've got a CH bond. Now, I mentioned earlier on that H and C are not largely electronegative in our last video. and that is an exception. So even though, yes, it's basically right next to N, H and C is the cutoff point. That's the line we draw where we say that's not polar. So H and C is similar enough that it's not polar. So if I just had this part of the molecule, only this part of the molecule has temporary dipole-induced dipole forces. This part of the molecule experiences permanent dipole-dipole because H and O are far away, and H bonding because it's H and O. So ethanol, again, another one of those molecules where it's a liquid at room temperature and we need to put energy in to be able to boil it. Right, I've got a table here for you guys to complete. Really, really simple. I know it looks overwhelming on the screen. I just want you to tick the intermolecular forces present in each one of these molecules. Look at what's in the molecule, look what it's bonded to, give it a tick. All right, let's move on. We talked about intermolecular forces before and how in temporary dipole-induced dipole forces, so things that don't have polar bonds, the only thing present is the temporary dipole-induced dipole force. So that shifting or that wobbling of those electrons where they go slightly positive and slightly negative, as you can see in this little diagram here, is kind of like wobbling. So I imagine it a bit like a water balloon, just kind of wobbling like back and forth. Now, the bigger that is, the bigger the shift of those electrons, the more temporary dipole-induced dipole forces it's going to create, the more energy it requires to boil it. So I need to put more energy in to break those bonds. And that matches. So if we have a look at here, we've got fluorine, chlorine, bromine, iodine, acetylene. This is going down group 7, so we're increasing the number of shells, we're increasing the number of electrons. More electrons means we're going to have more temporary dipole-induced dipole forces. It's a bigger molecule. It's going to require more energy to break. That's essentially what we're showing. Fluorine's tiny, acetylene is huge, and you can see that I need to get temperature to 400 degrees to boil acetylene, whereas fluorine has already boiled at minus 200, which means that a room is already a gas. And same with chlorine. You can see with bromine, it boils at 100. So at room temperature, it's still a liquid, but we need to heat it to break it, and that increases the trend. What I would like you to do is pause the video and have a look at completing this for 3 to 4 marks. Think about the things that we need. So remember the trend, what's happening with that trend, why is the boiling point going up? Explain that for me. This isn't cars. Right. The last bit. So this is something new that we've had to talk about, and I'm actually quite interested in this. And with water's got some really incredible properties, and one of those properties is that it's that ice is less dense than water, which sounds normal to you guys because you can imagine an ice cube floating in the water, a little bit like this, but that is almost the reason why we exist today. If the ice age froze over and ice was more dense, like most other things, the ice would sink to the bottom, all the water would freeze, and all life would die, and we wouldn't be able to continue. But ice didn't do that. It spreads apart, it freezes, and then it becomes less dense, and it basically surfaces on the top. Now, the reason for that is when ice or water freezes, what we're looking at is all these hydrogen bonding arranging themselves in a lattice. And that lattice structure is what spreads them apart and makes them less dense, I find it fascinating. So the ice is less dense than water. The reason being is those strong hydrogen bonds form a lattice that allows that water molecules to be less dense when solid. Simple as that. Now, the H bonds hold the molecules apart. H bonds are here because it's an OH. They're strong intermolecular forces, and they keep the ice molecules apart. In liquid water, the hydrogen bonds are constantly breaking and reforming, which is why it has that liquid flow, because the molecules aren't fixed in a simple position. They have some freedom to movement, but that's the difference between ice and water. And then we've got this concept of cohesion. So cohesion is molecules sticking together. So if you look over here, I've got this beautiful diagram. I am proud of it. And you can see I've got water molecules and then this like thing on the side. I'm not really sure. Maybe it's a wire. I'm not really sure what it is, but it doesn't really matter. So you got the water molecules, and between other water molecules, that H bond results in cohesion. It makes the water molecules stick together. So they're quite stuck together. And you'll experience this when you, like, say, for example, you're washing your hands and the water trickles down your arm even against the gravity. So what it's doing is it's adhesing, so this is this part, to your skin, and it's sticking together in a bead and like a string of water because of that cohesion. And that cohesion is also how like straws work. So when you suck up water in a straw, then it also goes up as well. So those forces are there to keep the molecules together and makes it strong enough to create this cohesion. Now, I also like this example because it explains the next point, which is a high surface tension. The high surface tension is due to these strong cohesive forces under really, really high tension. So if you imagine all the water molecules holding each other's hands using H bonding and temporary dipole-induced dipole forces and permanent dipole-dipole forces, they're all keeping themselves together. And because they're doing that, it means things like leaves and insects can land on that surface and not sink because they can't break the surface of that. They can't break the tension on that surface. So they're basically standing on that water. So they don't actually apply enough force to break that cohesive force, so they can actually float and run across the water. Yes, there are spiders that can run across the water, and yes, it's terrifying. So for this table, it's just a simple understanding of information, and I would just like you to fill in some of the gaps. So ice is less dense than water. H-bonds hold the molecules apart. Ice has a high boiling point due to, I missed this point, due to those strong hydrogen bonds between the delta negative O and the delta positive H, and therefore requires lots of energy to boil. As you imagine, at room temperature, 25 degrees, water is a liquid. In order for us to boil it, we need to put tons of energy in to heat that thing up. Cohesion is molecules are sticking together. Water is attracted to other water molecules, and it's strong enough to create cohesion and a high surface tension. And that's basically it, guys. Right. Thanks for listening, and I will leave you with this. So this is just a summary of what we mentioned before. No tasks here, but I do need you to complete the rest of these pages. Right, really good job. Thank you for being patient. I'll see you soon.